Okay, so I'm going to look at the modern physics, and I'm going to do 2004 B6, and it says that a student performs a photoelectric effect and has this equipment, okay? And they have light of various frequencies, and they send the light to this photosensitive plate. Power supply is given to you. It's all connected in a circuit which has 2 meters, M1 and M2 is shown above. The student shines light of specific wavelength lambda onto the plate. The voltage on the power supply is then adjusted until there's no more current in the circuit. And this voltage is recorded as the potential, the stop potential. So we need to answer their questions. All right, so then it says the student then repeats the experiment several more times with the different wavelengths of light. The data along with other values calculated from it are recorded in the table. Indicate which meter is used as an ammeter and which meter is used as a voltmeter by checking the appropriate spaces below. So we know that this is an ammeter because ammeters are always placed in series. This one is a voltmeter because voltmeters are always placed in parallel. Because in parallel the voltage is the same, and in series the current is the same. So this is parallel to both the power supply and this photosensitive metal plate. All right, so that takes care of that one. Okay, then it says use the data above to plot a graph of K versus F on the axis below and sketch a best fit line through the data. So let's see if we can figure out if I can do something like that for you. Not real sure, but I'm certainly going to try. So I came over here and I said, all right, well, I looked at when the frequency was, all right, I got to get my values. When my frequency was 7.5 times 10 to the 14th, and that my stopping voltage was 0.65. So I found that one, and 0.65 would be about in the middle. So I made a dot right there. And then I did the next one that was a little bit more than 7, and the stopping was somewhere between 4 and 5. So I put a dot there. And then I had something that was about 6.32, and the stopping for that, oh, I lied. I had one that was about 6.7, and the stopping was 0.3. So I had a dot there. And then the last one was the 6.32 that I was trying to do a minute ago, and it had a stopping of about 0.15 EVs. All right, and then I drew a best fit line. And if you had a ruler and a piece of paper, it'd be a whole lot easier, but I'm just going to make do right there. So there's my best fit line. Okay, then it said use the best fit line you sketched in Part B to calculate an experimental value for Planck's constant. So I said, well, I know that KE is equal to HF minus phi. All right, so that really looks like Y is equal to MX plus B, where this is my slope right there, okay? So I said H was equal to delta Y over delta X. Y was my change in the stopping potential, so I used 0.65 EVs minus 0 EVs. And then I divided that by delta X, and when I did that, I got delta X to be about 7.5 times 10 to the 14th. Hertz minus 6 times 10 to the 14th. And this is a lot easier to do on a piece of paper where you can actually draw your little triangle, but my little triangle is going to go from here to here. So there's my delta Y. And here was my delta X. So when I calculated my H value, I got 4.3 times 10 to the minus 15th EV seconds. And that's pretty darn close. I think it's 4.14 times 10 to the minus 15th. So I think we're doing pretty well with that. All right, so I got rid of that, and then I came on down. First I have to go to the mouse. My apologies. All right, so we did C, and then it said, If the student had used a different metal with a larger work function, how would the graph you sketched in Part B different, and explain your reasoning? So I said the graph would have the line shifted to the right. Line of best fit shifted to the right. Oops. Looks terrible. S-H-I-F-T-E-D to the right. I apologize. This line of best fit would be parallel. To the original line. To the original line. So slope would still be h, the Planck's constant, since it's parallel. Okay, now I'm going to go back and read it again. Different metal, larger work function, so that little phi value would have been greater, and that phi value would indicate that's my x-intercept. So if I moved it farther to the right, my phi value would be greater, which makes complete sense. All right, that's all they wanted you to do on that one. That wasn't too big of a deal. All right, so I'm going to clean this mess up, and I'm going to go on to the next one. Okay, this one says, light is shined on a photoemissive surface of work function phi is equal to 2 electron volts. And the electrons are released with a Ke of 4. All right. So the stopping voltage is the voltage that's necessary to get rid of all of this motion. So the stopping voltage would occurred when the Ke max was 4 electron volts, and so I know that W is equal to VQ. W is the work or the energy, so 4.0 electron volts, and that's supposed to be a 0, my apologies, is equal to V times the charge of an electron, we're going to call it E. So if we divide those out, then the stopping voltage would be 4 volts, because that's the amount of electric potential it would take to bring those lovely little particles to a stop. Get rid of that Ke. Okay, then it says determine the energy of each of the incoming photons in electron volts and in joules. All right, well, that's a piece of cake, so let's do that. So I just said that energy of the photons is equal to Ke max, or K max, whatever you want to call it, plus V. So I know that that is 6 electron volts, because this one was 4, and this one was 2. So I gave them my answer in electron volts. Now they want me to put it in joules. Well, 1 electron volt is 1.6 times 10 to the negative 19th joules. So if I did that correctly, I could say that that's going to be 9.6 times 10 to the negative 19th joules. All right, incoming frequency. So frequency is going to be equal to, well, I know that E is equal to HF. So the energy of the incoming photons divided by Planck's constant should give me the frequency. So frequency is going to be 9.6 times 10 to the negative 19th joules. You could do it in electron volts if you wanted. I'm just so used to joules. Divided by Planck's constant, 6.632 times 10 to the negative 34th joule seconds. Joules will cancel. So when I divide that, I got my frequency to be 1.5 times 10 to the 15th hertz. So that one wasn't too challenging. All right, then I flipped the page over. And there was one more. And I said, yippee skippy, let me do that one. So let's get rid of all this stuff. And we'll use the mouse and we'll go on down and figure out this last one. Because I don't think it's very hard either. All right, so here's what I said. An electron in the ground state absorbs a photon which causes the electron to be raised to the second energy level. Determine the following for the absorbed photon. So we wanted the wavelength, so I said, well, E is equal to E2 minus E1. That'll be the energy of the photon. Alright, so E2 is negative 5.74 electron volts minus my negative 10.38. So when I did that math, I got 4.64 electron volts. And I said, well, I want lambda. So I know that E is equal to HF, Planck's constant times frequency. But HF can be rewritten as h, speed of light, divided by the wavelength. So the wavelength is going to be hc over E. Alright, so I had my h. This is in EVs. I'm going to leave it in EV. So this is going to be 4.14 times 10 to the minus 15th electron volt seconds. This is 3 times 10 to the 8th meters per second. And then I divided that by my energy, and my energy is 4.64 EV. So the EVs cancel, the seconds cancel. I'm left with meters. So my wavelength that I calculated was blah, 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 267.24 nanometers. Alright, so that wasn't any big deal. Okay, so let's mouse and get to the rest of this. Oh, they wanted my frequency, so if I did that, I could say my frequency is equal to C over lambda. And I already did that on this piece of paper, my apologies. 1.12 times 10 to the 15th. Hertz. Alright. Then it wanted to know whether the absorbed photon was in the visible range. Well, to be in the visible range, we know that our light needs to be in the range of 400 to 700 nanometer for my wavelength, and so no, not in the visible range. Not in visible range. Alright. Then C says the electron absorbs a second photon of energy 10 electron volts while it's in the second level. Find the kinetic energy of the electron after it absorbs the 10 electron volts. So I said, well, I know that my KE is going to be the 10 minus the 5.74 electron volts, because that's what the energy is required to get out of that second thing. So I want to shoot out that electron, and the remaining energy that's going to give it that velocity is 4.26 electron volts. So there's the kinetic energy. Alright. And if they didn't want it in electron volts, but they wanted it in joules, we could convert that. And it doesn't say, but I'm going to do it anyway. 1 electron volt is 1.6 times 10 to the minus 19th joules. So if I multiply 4.26 times 1.6, I wind up getting 6.82 times 10 to the minus 19th joules. Alright, so I think we're done with the modern physics packet. I'm going to put it on YouTube.